So my name is Frank McKenna. I'm here at UC Berkeley, working for the Near East Sim Center. In this video, I'm going to talk about arrays and memory allocation. So we've seen before what arrays are. Arrays are fixed-size sequential collection of elements, all of the same type. They're contiguously stored in memory. We access them using either indexes inside of square brackets or by dereferencing pointers. To declare arrays where we know the size at compile time, we use the following notation. We give it a variable name, give it an associate with a specific type, and then we specify the size inside the square brackets. If we need to initialize the array in a comma-separated list of values inside curly braces, we can initialize the array. Now this works where we know the size of the array at compile time, and there are many situations where we do not know the size of the array. And there are other times where we want to create an array inside a function, but we want the array to exist when the function has popped. Now this wouldn't happen if it's on the stack, so we need this array to be allocated from the heap. To allocate memory from the heap, there's two functions available. These functions are malloc and free. Malloc and free must always be used in pairs. If you malloc something, you should always free it. The reason for this is you can run out of program memory if you don't free up memory that you no longer need, and you can also create page faulting in your program, which is the kiss of death. Performance will degrade dramatically if you start page faulting. So again, free and malloc are the two functions we're going to use. They're always going to exist in pairs. Free is the function to free up memory, and malloc is the function we use to obtain memory from the heap. Malloc takes a single argument, the number of bytes, to allocate. Malloc returns a void pointer, so what we have to do is cast it to the type pointer, whatever the type, where the type can be int, double, whatever type we're trying to create. And this, what I'm doing right here, is basically defining a variable. The pointer is going to be a pointer to a specific type, and the type again could be a float, double, or an integer, or whatever other type of variable we're looking at. So here is a very simple example of using malloc and free and the pointer variables. I'm not going to go into great detail about what it does. You should now start be able to understand what these programs are doing. But basically, I'm declaring a pointer array1 points to a double array. I'm initializing it to 0. Here is where we're using malloc. I want to create an array of size n, where n is come in from the input. So it's n times size of double. Remember, malloc allocates bytes, but double array doubles are 8 bytes. So I need to get the size of double. To get the correct byte size array, I need to cast from a void pointer to a double pointer, and then I can do my assignment without the compiler complaining. I'm putting memory into the array, I'm spitting out the array, and I'm spitting out the address of the array. And finally, when I'm done, I'm freeing up the array. So this is the result of the program. If I run it, I get 0, 1, 2, 3, and then I get my memory addresses. As you see, they increment by 8, 8 being the size of a double. So that was one very simple example. This is a slightly more convoluted example, and all I'm trying to do in this one is demonstrate there are other ways of assigning pointers. So we have array1 pointer as before, we malloc as before, we print the value as before, and then we free as before. So what I'm introducing in this program is two new pointers, array2 and array3. Array2 and array3 both point to an array of doubles. So here's where I'm doing my assignment. I'm just saying that array2 is equals to array1. So what this will do is copy in memory into array2 whatever is currently in array1, which is so happens whatever the address that was returned from malloc. And for array3, I'm assigning it initially the address of the first component of array1, which will also should be the same thing as array2. I'm going to spit out the value for that when I dereference the pointers, array2 and array3. I'm incrementing the pointers inside the for loop. and I spit out everything, and you'll see if I spit it out, I get the exact same thing. So this really is just to show you there's multiple ways to find the initial array pointers. This is a even more convoluted example. Here we're introducing the notion of a double pointer pointer. So what is a pointer pointer? So matrix 1 is a pointer, so it's an array of something. So here is matrix 1, and what is an array of? It's an array of pointers to arrays. So here's matrix 1. The first component is a pointer, it points to an array. The second component is also a pointer, it points to a second array. It's a different array. So how do we allocate this convoluted matrix? Well, we're using malloc again. It's n times the size of double pointer. Double pointer because these are pointers to an array. Inside the for loop, we have to allocate each of these arrays. So this is what I'm doing here. It's n times now size of double. It's not double pointer, it's now size of double because these are now doubles. And into these arrays, we're going to initialize the values. And then finally, we're going to print out the values. And the important part again, for every malloc, there's got to be a free. We have 1, 2 mallocs, therefore we have number of frees. We need to first, when we allocated these things, we allocated this one first, and then we allocated 1, 2, 3, 4. To free them up, we have to do it in reverse order. We first free these arrays, and then we can free this array. If we free this array first, we no longer have these pointers available to free these arrays. They don't necessarily exist anymore. So that is that convoluted example. And here again is that convoluted example trying to create a matrix. We of course do not want a matrix in this form that is shown there. We want a contiguous array of values. So when we create a matrix, we want a column majored ordered row of elements in a single contiguously arrayed. So this is how we would allocate it. It's num rows times num columns times the size of double. So this is what we're going to do when we allocate a matrix. Probably in your homework when you're doing a matrix vector multiply, you want to allocate it like this. And here's where I'm putting the values into the array. I loop over all the rows. So there's 4 rows or 3 rows in this example. And I go through each column. So 3 rows, 3 columns, and I enter the component. Now you see, I'm going down each row and then across each column. So down each row and across each column I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. Column major ordering, we're going to have 1, 4, 7. So we're going to have all these cast meshes. I'm not going to be taking advantage of the spatial locality that we talked about in the first presentation. So this is really a bad way to enter the values into this matrix. A better way would be to go 4, 7, 2, 5, 8, 3, 6, 9. So this is how we would order it. And this is could be a slightly slower way than actually accessing it with the data pointer. So we just set the data pointer to point to matrix 2. For example, if this was matrix 2, we'd send it pointing here, and then we just go through the components, incrementing the pointer by 1 each time, and filling in the array components. Now, special problems we have with character pointer and strings. There's no string type in C, but there is a functions we can use in string.h. These are string length, string copy. So now if you think about a string being an array of characters, there is no way that string length and string copy could know where the string ends to do the copy or to figure out the length if it was just a bunch of characters. So what we have to do is add at the end of a string a special character, namely /0. That's done to mark that this is the end of a string, so we can actually print out a string. And because we have this special character that doesn't actually show up in the string length, what we have to do is make sure when we malloc, we need to allocate of size +1 so that the string copy will actually copy the hello, plus it'll actually also copy the /0. So we have to make room for that /0 when we malloc a string. And here's another special example I thought I'd demonstrate. It's actually very similar to our matrix example. So I've been using this char pointer argv on all my mains. So what is a char pointer argv? Well, argv is an array. It's an array of pointers to strings. So this is a character pointer. Character pointer is an array of characters that was going to end with a /0 because they're going to be strings. So this is what argv is. Argv is an array of pointers to strings. So at the end of yesterday, we talked about program design, and if we were using a vector and matrices, we'd have put all the functions in one file. And I showed you a main which used a vector, and this was the vector. And we had this data pointer, data1 pointer, was our pointer to our array of doubles of size 10. So I didn't actually show you what those files were. So let me show you what is in my vector. You'll see my vector.h. There we have that malloc. So here's an example of where we want to create an array inside a function, and we don't want that array to go when the function has gone. So this is an example of why we need malloc. So let me also show you a little bit of argv. Oops, I'll just call it argv. So include standard io.h, include standard led.h, include string.h, int main, int argc, char pointer argv. We all now know what argv is. Return 0. Here's our main function. So now let us play with argv. So for int I equals 0, I less than argc, I plus plus, spit out the contents of argv. So printf, we'll do %d or %d, %s/n, and we are going to spit out I and argv I. Okay, this is our main program. Basically, it's going to loop over all the arguments that are passed in when the program's run and spit them out to the terminal. Now we're going to run that with hello Frank, go to bed. Oops, didn't like it. Yes, fprintf, we haven't showed you that one yet. Oh, not a problem. See the errors? I'm missing the semicolon. I've got a comma instead of a semicolon. As I say, the compiler will show you all the errors. gcc./ There we go. So there we have argument 0 is the first component is that program name, and then the other are the different arguments that are passed in. And then we can use the string functions to, say for example, argv I. So we'll get the length of the string. We could create a new string, char pointer new string equals char pointer malloc length plus 1 times size of char. Size of char I don't need to put in here because size of char is 1, but I'll just, for consistency with what I presented, let me just throw it in there. And then I'll do a string copy. Destination is new string. source is argvi. So let me put in the %d, %s. So after I will put in the length. And after argv, we will put in new string. And to be a good programmer, I will put in, wait for it, I'm going to put in free, new string. Oops, there we go.